I feel magnanimous, so let's do that. Do we have Jake? All right.
Do you know how our first math test?
There you are. What's this?
Do you know what we'll have our first math test?
Test. We are getting close. I'm guessing probably I'll give it to you Wednesday. We'll see how we go today. We're in 1.4. We got 1.5 to do. After that, I'll give you your test. So I think it will probably be Wednesday. Okay. Any other question? Good question, by the way. All right. Then, here is where my memory was that we left off in my mark in the book. I wouldn't even trust my memory. One-sided limits and continuity on a closed interval. That where y'all had it? Top of page 76, chapter 1, limits and their properties, 1.4, continuity and one-sided limits. So this is this one-sided limits and continuity on a closed interval. All right. Any questions on anything we've covered so far? Okay. So, to understand continuity on a closed interval, which I thought that's what we've been doing all along, you first need to look at a different type of a limit called a one-sided limit. Okay? For instance, a limit from the right, or the right-hand limit, means that as x approaches your c, whatever that value is, from values greater than c, coming in this way, sorry, I pointed the wrong way, I was going to the right. This limit is denoted by the limit as x approaches c from the positive side of c. C may be negative, but from the plus side of c, as it approaches it from the right-hand side of c, of f of x, if that limit exists, then that's given whatever the value is, L. Okay? So, if here's your function, okay, and you're allowing x to approach c from the right, sure enough, looks like there's a limit there. Of course, it looks like there's one from the left too, but the limit as x approaches c from the right, this is what it means. As x is closer and closer to c from the right-hand side, the positive side, then the limit is approaching this value right here. It's getting closer and closer and closer to that value, the closer x gets to c. Okay? Fairly sort of obvious in a graphical type way. Similarly, the limit from the left, or the left-hand limit, means that as x approaches, here we go again, c from the values less than c, from the left-hand side, from values on the negative side of c, this limit is denoted as limit as x approaches c from the left. That's what the minus, superscripted minus means, of f of x is equal to L. And sure enough, same function, as x approaches c from the lower side, that the left-hand side, side's more negative than c. Okay? X approaches here, the function is again approaching that limit L as x approaches c from the left. Makes sense, hopefully, right? Any questions? Okay. Now, one-sided limits are useful when you're taking limits of functions involving radicals. Okay? Remember, the square root of x. You can't approach x from the negative side, but none of those values are defined there. You can approach it from the positive side. So here's the example of that. For any even n, then the limit as x approaches c from the positive side is, the nth root of x is indeed 0. You can't leave off the plus sign here because it doesn't exist from the left. It does exist from the right. Because you can't approach, you can't take an even root of a negative number. Ever. In the real number system. I'll put it that way. In the real number system. Okay, so here's example 2, middle of page 76. Find the limit of f of x with f of x equal the square root of 4 minus x squared as x approaches negative 2 from the right. Okay? Now, let's write it down first. Hopefully you will recognize how it looks and whether it looks right or not. How would I write that? Limit LIM as -2 from the right. Which, how do we indicate that? The plus, a superscripted plus there. Perfect. Square root of 4 minus x squared. You put your f of x in there. And what would be your first approach to evaluating it? Plug it in, and see what happens. Well, as you approach -2 from the right-hand side, what would that be? We plug a -2 in for x. -2 squared is 4, and then 4 minus 4 is 0, and the square root of 0 is 0. You certainly can do that. Can you do the same? Is it Frank?
Cedric.
No, Cedric, got it. I have a Cedric in my Tuesday, Thursday class, and I never think of you as Cedric because he looks very different. Okay, never mind, sorry about that. Okay, so you can approach it from the positive side by plugging in. And anything greater than -2, like -1, yeah, that's no sweat here either. But you can't approach from the left-hand side. And is this Frank? Yeah, okay. I knew if I guessed it long enough, I'd get it right. Okay, good. Okay. Good deal. You can't plug, even if this was a minus sign here, you plug it in and it works, but it doesn't move anything to the left of it. If you tried plugging the -3 in there, ain't not going to work, okay? So that would be a 9, 4 minus 9, -5. No, it's not going to work. And anything past -2 on this side will not work on the left-hand side. From the positive side, yes. Okay? Now, while we're here, can someone give me another thing that x could be approaching, and it would still be a limit of 0. Second? +2. Just +2? Second? With the positive, is that what you said? Okay. How about it, folks? As x approaches 2 from the positive side, like 2.1, would that be close enough? 2.1 squared is going to be something like 4.01 or something like that, right? No, not that, but something like that. And then, no, it's not going to work. Can't approach 2 from the positive side. Not going to work there. What would work?
Approach it from the negative.
Approach it from the negative side. That will work, and that will be a correct answer. Okay? And they show in your text the reason for that, and I will just do a lousy rendition of it. This function, okay, but you could do it too. What is f of x always equal to? At least in most of our systems. From pre-calculus algebra, I told my students it's the most important thing to remember in pre-calculus algebra. F of x equal, none of you were in that, were you? Okay, good, I'm glad no one. Glad that there's no one here that wasn't and forgot it. Okay, it's y. F of x equal y. Thing to remember in pre-calculus algebra, this is y. So if you put y is equal to the square root of 4 minus x squared. What's messy about that? The messiest thing about it. Square root symbol. How do we get rid of it? Second, square both sides. So that gives us y squared is equal to what? 4 minus x squared. And then what could you do, especially if you like all the variables that hang together, all the constants not to? That's a dumb question, wasn't it? But what happens if you add x squared to both sides? What do you get? X squared plus y squared equal 4. And what does that describe? Anyone recall? A what? Circle of. What's the 4 represent? Second? A little louder, I heard something.
The radius?
Radius. Squared, exactly. So the radius would be 2. That would be a circle of radius 2. So if I were to draw this here, a 1, 2, 1, 2, 1, 2, 1, 2. I don't draw circles very well, but something like that. Is that a function? No, I took a function up there and fiddled with it some and made it something not a function. Why is that not a function? Vertical line test flunks from -2 to 2. Fails. What was that actually describing?
A semicircle.
The semicircle from here to here, the top half, not the bottom half. Okay? And this is a lousy rendition, but okay. That's what we've got. So you see from this, and this is in the book too, by the way, x can't approach -2 from the left-hand side. Not allowed. Can't. The function is not defined there. No value there. It can approach it from the upper side, which is what we were doing here. X approaching -2 from the positive side. But over here, x is approaching what? 2 from the negative side and cannot approach it from the positive side. X cannot approach 2 from the positive side because there's nothing out there. The function is not defined there. So that's why these two work, the other two don't. Okay? Does that make sense? That makes it necessary to use one-sided limits in circumstances such as that. Now there's others. Oh, let's see how they did it. Oh, I didn't have to draw this. I forgot. They were going to draw it for me. Wasted time and effort. There it is. It's shown in the figure. They started with drawing the graph of that thing, which a graphing calculator would have done for you as well. But there's the graph of it. It is a semicircle. I showed you how you could get that. And the limit as x approaches -2 from the right-hand side or from the positive side is defined. It is not from the left. There's no function over here. Never will be in the real number system. And similarly, I threw in x could approach 2 from the left-hand side, the minus side, but it could not approach it from the right-hand side because there's no function over there. It doesn't exist. Okay. Make sense? All right. And they left off example 3. Sorry. Let's go back and do that fairly quickly. I don't know if you've run into this. Not one of my favorite functions of all time, but the book loves them. Find the limit of the greatest integer function, that's f of x, is equal to this funny looking little symbol here. I call it a double bracket. I don't know if that's what they actually call it, but that's what I call it. Okay? A double bracket, and x or some value in there is in it. Oh, I'm sorry. Did they have this? Oh, yeah, I'm sorry. I didn't look far enough. They have this work for us. One-sided limits can be used to investigate the behavior of step functions. One common type of step function, though I don't find it really all that common, is the greatest integer function, which certainly is well, and here's how it's defined. Greatest integer function is the greatest integer n, so your output is going to be an integer n, such that n is always less than or equal to x. Okay? So, for instance, what's the greatest integer in 2.5? 2, exactly. Can't have a decimal in it because it's an integer, okay? That would be 2. What's the greatest integer in negative 2.5? Negative 3, because you always look to the left, okay, to see what the greatest integer is less than or equal to x, and negative 3 is the next thing left of negative 2.5, not negative 2, so sure enough, that's negative 3. All right, everybody got a pretty good idea of what it is? Here's what it looks like. No, it isn't. They're not going to show you what it looks like. That's what they left off. Okay. So let me go back. All right. Find the limit of the greatest integer, f of x equal greatest integer in f, as x approaches 0 from the left and from the right. Okay? So we would express this as the limit, you tell me, as x approaches 0. Which one are you doing first? And which would that be? Negative, superscript negative, of this funny looking little symbol here. I call it a double bracket. What would that be? If it's helpful to draw the graph, draw the graph. Okay? Now, we'll start at 0. Greatest integer in 0 is 0. Greatest integer in, say, 0.1 is? Okay, 0. Very good. 0.5? 0. 0.9? 0. How about 1? Okay, this is 1 here. What's the greatest integer in 1? 1. You jump up here. So you had all these here. Everything, even 0.999999999 is still 0. It'll come back. I say it will. Okay, it's winking at you. Okay. But it doesn't include 1. Okay? Up here it jumps up to this one. And then does this number from now on. If I could get it to right. Goodness gracious, being wacko today. This is what the greatest integer looks like. And over here, what if you had a negative 1 here? What's the greatest integer in negative 1? Negative 1. Okay? Negative 0.9. Second?
0.
Always look to the left. Yeah, it's negative 1. And on to 0.01. Negative 0.01. Negative 1. How about 0? Up, jumps up to 0 there. So you see it keeps doing this kind of motion forever. I'm not filling in all the details, but you get the general idea, I hope. Okay? So, what's the limit as x approaches 0 from the left-hand side?
X minus 1.
I would say x minus 1, just minus 1. Is that what was said? That would be negative 1. See, it's any of these. You're approaching 0. X is approaching 0 from the left. Then the value is here, here, here. It's minus 1. And the closer you get, it's still minus 1. It's not equal to minus 1, but it's approaching. So this is an example. You can't plug it in. You have to think through and get closer and closer and closer. Yeah, the limit is negative 1, but the value is not negative 1. On the other hand, what's the limit as x approaches 0 from the right-hand side, because they say go both ways, of greatest integer in x? What would that be? 0. Because, see, you're getting closer and closer to 0 on the x-axis, and the y value is 0 all along there, and it's actually equal to 0 there. This one you could have plugged in, but this one you couldn't plug in. If you plugged in, you'd have gotten 0. It wouldn't work, but the limit is negative 1. So approaching 0 from the left, the value of the function is -1, approaching 0 from the right, the value of the function is 0. All along there. I mean, 1. Yeah, 0. I'll say that right. Okay. Great. Okay. Interesting. Mathematicians love this function. I'm sure it has some practical value somewhere. I'm certain it does. And this, by the way, is called the step function because you see the graph walking up steps, right? Okay. Now, there's many other step functions that I find a lot more practical. For instance, have you ever mailed a letter? Anybody? I know you young people, you don't know what I'm talking about there, but I'm not talking about emailing. That's just a send button. Actually, those things you put in the envelopes, you remember those? That you read about them in the history books, right? Now, what if it's a big fat letter? You gonna stick that forever stamp on it? You all even know what a 24-cent stamp is, do you? All you know is forever stamps, right? Will that work? Big, fat, thick thing, several pages?
No.
No, why not? Say again? Yes, you do it by weight. Anything up to an ounce is going to be whatever it is these days. Is it 54 cents, 50 cents? I think it went to 50 recently, didn't it? Who knows? All we use is forever stamp. If anyone ever mails a letter, I believe it's 50. So from 0 ounce, and guess what? Have you ever mailed a 0 ounce letter? Just did, and it didn't cost a thing. Okay. No, you don't. So that's going to have an open circle at 0, because you can't even have one. And then it's going to be 50 cents up to an ounce. And at 1 ounce on the nose, it'll be 50 cents. But then when you go to 1.1 ounces, you jump up to whatever the next increment is. I don't know what it is, another 43 cents or something like that. I just made that up. But anyway, and so that's a step function. But on that step function, your open circle is on the left-hand end, your closed circle on the right. But there's a very practical step function. Used to be things like cell plans and even regular phone plans, if you, I guess, but at least cell phone plans. Up to so many minutes, it was one cost, and then it jumped up to anything past that was another cost. I think they're all pretty much uniform now, I think. Or maybe there is a limit, but people seldom reach it, okay? Or data minutes, yeah. There used to be all sorts of stuff. So there's lots of examples of step functions out there in the real world. I've just never used the greatest integer function very much, okay? I can't remember if I've ever used it, but that's beside the point. Does that make sense? And with a step function, one limit from one side of that, the line of demarcation, whatever it is that's creating your step, will be this on this side, this on that side, okay? Same here, whether the open circle, wherever the open circle is, the limits are not the same. In between, as x approaches 0.5 from the left or right, what would that be? As x approaches 0.5 from the left or the right, what would that be? 0, of course, because at 0.5, it's going towards 0 here, and it's going towards 0 there. You have to get close. You know, you can't be out here and going to, you have to be fairly close. And that's one of those weasel words there, as it approaches, okay? You mean from a pretty close vicinity. All right, enough of that. Now, when the limit from the left is not equal to the limit from the right, the two-sided limit cannot exist. Cannot, just like we saw. The next theorem makes this more explicit. If f is a function and c and l are any real numbers, then the limit of f of x as x approaches c is l, is that real number l, if and only if the limit from the left is equal to the limit on the right. Stand up, sit down, 5, 5, 5. No, that was something else. Okay. That has to be that way. Just like I said, 0.5, that would work on the greatest integer function, because limit from the left, limit from the right, still 0. But any of the integers, okay, left is going to be 1 less, and from the right will be 1 more. Does that make sense? Okay. Now, this concept of a one-sided limit allows you to extend the definition of continuity to closed intervals. Okay, yeah, we were wanting to do that, weren't we? Basically, a function is continuous on a closed interval when it is continuous in the interior of the interval and exhibits one-sided continuity at the endpoints. Okay? Now, yeah, all that is true. It doesn't have to be only one-sided, but it does exhibit one-sided continuity at the endpoints. Okay? Here's the example. All right. Function f is continuous on a closed interval from a to b, closed interval. That means that this is a solid circle, that's a solid circle. No open circles on either end. Okay? Continuous on a closed interval. When f is continuous on the open interval, a to b, now you could have open circles there, okay? And the limit as x approaches a from the right-hand side, from the positive side, if that is equal to f of a, that means it's closed there, okay? And if the limit as x approaches b from the negative side, if that is indeed f of b, yeah, if that fits, if this function gives you the value here and here when you approach it from a from the right and b from the left, then this is, the function is continuous on the closed interval, okay? You may not know these or even have any, you do not even care about what values they are there, but if they do exist and meet these two criteria, then it's continuous on a closed interval. Open interval could be on open interval if these are unknown, or if they're known, they'll have some value down here or up here or anywhere else, either one or both of those, then that would be open on continuous on an open interval, but not on the closed interval, because the limit, the value at a would be down here or up here or somewhere other than this function f of a. This defines f, and if those meet the criteria, it's closed on the closed. It's continuous on the closed interval. Okay. Any questions? Not a huge issue, and why are we spending so much time on it? You say, okay, because you paid for it. Okay, never. All right, here's the thing. Continuity on a closed interval. Discuss the continuity of f of x equal the square root of 1 minus x squared. Can anyone discuss that continuity? I know that's what you woke up this morning thinking about, the continuity of that function. What would you say about it? Okay. Your domain is excellent, plus 1 to minus 1. That's a good place to start. Domain of this f of x, which is that thing, is, okay, I'm going to put minus 1, plus 1. I'll put a comma between. Second?
The range is going to be 0 to positive 1, right?
A little louder.
The range is going to be 0 to positive 1?
You're absolutely right on that too. Range of f of x is 0 to positive 1. I don't have those written quite right though. I need some sort of grouping symbol on either end. What needs to go there? What?
On the domain, it's going to be a bracket.
Bracket on the left and bracket on the right. Range.
It's going to be
Bracket on the left. Bracket on the right. Okay? Now, when we're talking about continuity, we really don't we look at the values of the range, but we really don't care. What we're talking about is domain type values. So what would you say now? Discuss the continuity of f of x. Is it continuous anywhere in that domain? Yes, in that domain. And that is a, what kind of interval? Closed interval. So that is continuous on the closed interval minus 1 to 1. Or in any closed interval inside of minus 1 to 1. Minus 1 to 0. 0 to 1. Yes, closed is continuous, any of those. How about negative 2 to 0? No, okay, not even defined. It's outside the domain, okay? So as long as you're within that, you can talk about continuity. Outside that, it makes no sense because values are not even in the domain. So that is continuous on the closed interval, minus 1 to 1, in any closed interval contained in that. Okay, I don't think the book makes a big deal about the second part, but let's see what they do. The domain, just like Bill stated, is minus 1 to 1. So at all points on the open interval, minus 1 to 1, the continuity of F follows from theorem 1.4 to 1.5. Those are indeed true. And they don't say anything about the thing, but it's, why didn't they go on and say, the domain is that, but it's also continuous there, okay? Oh, they're just repeating this. Here's 1.4 repeated again. The n be a positive integer, and what is our n there? I don't see an n. See an n, that's a network. What's your n? 2. Okay? Now, in all the rest of mathematics, I think, pretty much, if you don't see a number, like I don't see a coefficient for the x here, so what do we understand it to be? 1, with a minus in front, be a minus 1. And they don't have one anywhere else here on this page, but, oh, right down here. I don't see an exponent for that x, so what would that be understood to be? 1, okay? If you don't see a coefficient or an exponent, you understand it to be 1. Except with radicals, you understand that to be, if you don't see an index for a radical, you understand it to be 2, not 1. You don't ever take the first root. That's not even a root, really. Okay. All right, so that's a 2. So if n is a positive integer, in this case 2, positive integer fits, the limit below is valid for all c when n is odd, and is valid for c greater than 0 when n is even. So that means that just defines your domain. Okay? If n is odd, all real numbers. If n is even, from 0 positive. Okay? 0 less than or equal to x, less up to infinity. Okay. Now, that's with x in there. And then theorem 1.5, which we just did, if, oh, no, this was the composite function, limit or composite function. F and g are both functions such that the limit is x approaches c of g of x is L, and the limit is x approaches L. If f of x is f of L, then the limit of f of g of x is the f of the limit of g of x, which is L, and that's f of L. So, what did that have to do with this problem here? Yeah, your g of x was your 1 minus x squared. So as long as that has a limit, which means you're between minus 1 and 1, like Bill said, then you have a limit. And since you have a limit there, then f has a limit too, as long as x is in between those. So your comment about the range there is quite good there, because that's the g. The range for the g, 1 minus x squared, is 0 to 1. Okay. Carrying on. Moreover, because the limit as x approaches minus 1 from the left is 0, which is f of minus 1, and they finally got to the answer. The limit as x approaches minus 1 from the 1 from the right-hand side is also 0, then, because this one is approaching from the left, that one from the right, and they have the same values of the F function there, then this is continuous on the closed interval minus 1 to 1. So they finally answered the question. F is continuous on that closed interval. Now, they don't say it, but any closed interval included in that, it would also be continuous. All right. They're skipping examples 4 and 5, I believe it is. Yeah. So let's go catch those if we can. All right. No, we already did 4. 5 is the one we didn't catch. All right. Here's example 5. This is on page 78. It's not my law. Okay, no. This is a guy whose last name was Charles. Charles's law on absolute 0. On the Kelvin scale, absolute 0 is temperature 0 K. Now, what's something you notice about that temperature 0 K that's a little different from most other scales? It doesn't have a degree sign. Kelvin temperatures never have a degree sign. They're just 7K, 385K, 0K, whatever, never put a degree sign. Fahrenheit, Celsius, yes, put those degree signs. But Kelvin scale, no, do not. Okay? That's absolute 0. Although temperatures very close to 0K have been produced in laboratories, absolute 0 has never been attained. The third law of thermodynamics states that the absolute 0 may be approached but never reached. Now that's a theory, okay? We've never been able to disprove it, and a lot of people think it's fact, but it's still just a theory, okay? In fact, they say here, evidence suggests that absolute 0 cannot be attained, okay? Part of that goes to quantum mechanics, which is pretty much a theory itself too, that you can approach a 0 rest state, but you can't get there, okay? That means there is not 0 energy, but minimal energy, and that nothing ever is down that low, okay? How do scientists determine that 0 K is the lower limit of the temperature of matter? And what is absolute 0 on the Celsius scale? How are were you expected to know that? And it's given here, and I guess the determination was the work of a French physicist, Jacques Charles, okay? And he discovered, and I think other people had noticed it, that when you graph the volume of a gas at different temperatures, a given gas, say, get your scale here. I don't know what temperature scale you want to use. At the time, they didn't have K. What's the temperature scale you want to use?
Celsius.
Celsius, okay. Okay, at some temperature Celsius, say 30, that would be a little warmer than room temperature, the volume of the gas would be here. Room temperature at 20K, or somewhere close to that, would be down here. At 15K, you keep going on down. At some point, you get to, Celsius, okay, 20 Celsius, 15 Celsius. At some point, 0 Celsius, which will not hit here. Yes, we will, sometime this evening, maybe around midnight or so, it'll get down to 0 Celsius. What is that? 30, yes, freezing point, 32 Fahrenheit. And it'll actually drop below that. They say it's going to get down to 27 or so sometime overnight, so it'll get down to negative. Well, that gas will continue to shrink in volume. This is the volume scale, here's the temperature scale. But you're over here in the negative Celsius here. If you keep lowering the temperature of that gas, and keep lowering the temperature of that gas, the volumes keep shrinking, okay? Until something happens. Anyone know it? Do what?
absolute zero.
Don't ever get there, okay? In fact, you don't really get very close. What happens before you even get very close to it? It turns to a liquid. You keep lowering the temperature of a gas, it ultimately is going to condense, okay? And at that point, the volume falls off really big time, okay? So it keeps going down until someplace at its vaporization point, condensation point, it actually goes, almost goes to zero. But you have these things, and those form just about a perfect straight line, okay? This is a given gas, okay? It's going down, heading somewhere, but not getting there. Well, let's choke a different gas, okay, at a given temperature. It might be here, and it might have a more gradual slope, but at some point it goes to a liquid as well, okay? They even past a liquid, it's going to go to a solid. If you get cold enough, everything will go that way, okay? But different gases, they all have different slopes, but guess what? Every one of those slopes is pointing to some common value down here. Never gets there because they all condense out long before there, but their slopes are all pointing to that zero cap. Okay? So, that's what Charles did, Jacques Charles. He experimented with several gases, so sure enough, with very careful experiment, all those slopes, even though they're different slopes, they're all pointing to the same point, and that's where he concluded this. Okay? Now they give you a table here for volumes measured in liters and the temperature measured in degrees Celsius, and they have it going downhill, and what they say is, they don't tell you this, but they ran probably a linear regression on these points, and they came up with a value of this, that V, volume as a function of temperature, is equal to 0.08213 capital T plus 22.4334. That's some pretty precise temperature measurements in my book, okay? Now, I'll tell you one thing, according to their table, I didn't print off the table, one thing fits really nicely. When T is equal to 0 Celsius, the volume was 22.4334. You can see that in the table right on the nose, okay? But then they fit these other points to that same linear regression line. So the question is, what would be the, again, Celsius temperature at which the volume went to 0, if you could get it to get that cold? I mean, if you could get it to remain a gas that long. So what would you do? Solve for T. How would you do that? Okay. Isolate it, get it by itself. How do you do that? First step. Second. Subtract, exactly. Subtract 22.4334 from both sides. Okay, these go away, and you have 0, I'm going to switch sides here, 0.08213 T is equal to negative 22.4334. And then what? Divide by, whoops, both sides by 0.08213. Okay, if someone brought a calculator today, do it to it and see what temperature you get.
You get negative 273.145014.
145014. Okay, now I'm not going to mess around with digits that small. Here we had 4 significant digits. Here we had 6. Best we could do was round to 273, negative 273.1. And a lot of times they'll say 0.15. And that's what that would round to too. That's pretty close to absolute zero. Okay? And this is degrees Celsius, by the way, which you do put the degree symbol, degrees Celsius, and that is considered. A lot of times I'll use negative 273, just as a round-off type number. But actually it is closer to something like that. And I don't know if they have a specific number of digits they can get it close to. And I've actually read this in either a physics or physical science book, that they've gotten to within a few millionths of a degree of absolute zero, but haven't gotten past that. And I asked, what kind of thermometer do you have that you can measure to a millionth of a degree? I can't even conceive of it, but I guess they can do it with that kind of precision, I assume. And they get close, never can get to whatever. However, if you with a millionth of a degree, you're going to have a lot more digits on that. So I don't know. That's what the statement said. Okay. So they rounded to negative 273.15. This is a math book, not a physics book. So they, frankly, I don't think they had the precision to go that. All right. Then they give another sort of example here. Liquid helium is used to cool the superconducting magnets, such as those used in magnetic resonance MRI machines, imaging machines, or the Large Hadron Collider, which is over in Switzerland, France, and maybe another country or two. I mean, it's a huge collider. And I think actually the Japanese use it on their bullet trains. They use supercooled cool condition on a goodness gracious. A superconductor. Supercooled liquid on superconductor. I was getting my supers all crossed up. And they actually elevate their trains off the track because the magnetic fields are very strong when you have absolutely no resistance, and that's why the trains can go so fast, because there's no friction at all between on the track. All you have is air resistance, and they try to control that as much as they can with streamlining and things like that. So those trains go very, very fast. Now, the temperatures possible for liquid helium, not gaseous helium, liquid helium, go down to negative 269 degrees Celsius, or 4.15 K. They can't get helium any colder than that because it's going to solidify. Liquid helium will solidify at 4.15, but that's awfully cold. Awfully cold. Okay. Just a little bit more of that type of thing. So this is not just theoretical. There are some real. Now, what can you tell me about then, why did they bring this up here? Okay. They never got around to saying it. The Kelvin temperature scale is not a closed scale. Okay. Anything greater than this temperature here, yeah, you can have a closed interval. But this one is open. You can approach it, but you can never get there. So the zero, absolute zero, is a one-sided limit, but you can't, it's not a closed interval. It's an open interval. I don't think they ever got around to saying that, but that's what they're aiming toward. All right, so let's move on to properties of continuity. Okay? I have a little guy over here on the left, Augustin Louis Cauchy. Okay? Now, if you find that it's a little unusual that his life overlapped the life of Jacques Charles, it's really not that strange when you think about it, because France was the superpower of its day in their lifetime. They spent more on research. Their hierarchy supported the scientists. They had the luxury of being able to study things that weren't really producing anything because it was. And that all came to an abrupt halt about what time? Anyone remember? Does the word guillotine bring anything to mind? French Revolution, around 1800 or so, plus or minus. I don't remember exactly the years of that. It was after the American Revolution, because the French came over. They helped us because they hated the British and they'd do anything to fight against the British. So they did, and then they decided to have one of their own, and theirs was not nearly as civil, you might say, as ours. They just went nuts and started chopping off heads too crazily. Okay, but anyway, up to that point, France was one of the honchos. So a lot of the work on magnetism, electricity, and this kind of stuff, you find so many French names there, and then they suddenly end. They don't end, but they cut off. Well, here's Augustin Louis Cauchy. I don't even know how to pronounce that last name. But anyway, if you want to write on him, he's a potential paper topic. The book can't be your source of the idea, but not the source of your thing. So here is properties of continuity. Theorem 1.11. If B is a real number, any old real number in the world, F and G are continuous at x equals C, well, where does that have to do with it? Then the functions listed below are also continuous at C. Whatever C happens to be. They really need to say it's a real number too. Not B, probably. But it could be. Okay. Scalar multiple, okay, if F and G are continuous at C, then the scalar multiple, B times F, where B is any real number times F, is also continuous at C. So you can multiply it by a huge number, you can multiply it by a tiny number, you can multiply it by a negative number, an irrational number, any kind of number, the function will still be continuous at C. The sum or the difference of those two functions will still be continuous. If F and G are both continuous at C, then the sum and the difference of those functions are continuous at C. The product function will be continuous at C, okay, F times G, and the quotient function, as long as G of C is not equal to 0, because you still can't divide by 0, no matter what kind of continuity you have. So as long as G of C is not 0, the quotient is also a continuous function, which will be very nice for us to use in the future. Now, a lot of times in more upper level math courses, you'll see not all of these, but at least these two put together and say, or kind of like they're put together, and the fact that the scalar multiple and the sum and difference are both done, you can say those fit linearity principles, and that will come up. You'll probably see that in later courses, but we're not going to worry about it now. Okay. Now, the list below summarizes the functions that you have studied so far. Hopefully you studied them, and that are continuous functions at every point in their domain. We know polynomial functions are, right? A polynomial function, by the way, is a sub n, x to the n plus a sub n minus 1, x to the n minus 1. These are just counters there that indicate this is the coefficient that goes with that exponent, and all the way down. Continuous everywhere. No limits on a polynomial function. Rational functions. Continuous everywhere as long as that denominator is not 0. Boy, that's a big requirement there. But as long as the denominator is not 0, continuous everywhere else except where the x that would make q of x equals 0. Radical functions, okay? F of x equals the nth root of x, okay? Now remember, as long as this is defined, so of course if n is even, x can't be negative. But as long as that's defined, you meet that criteria, these are continuous everywhere within their domains, at every point in their domains. That's the key. Polynomial functions everywhere. The others, you have to have those. Trig functions, sine and cosine everywhere. Okay? The others within their domains, but remember the domain cannot include your half pies here, or your whole pies here or here. Not included in the domain. So why do they say they're continuous everywhere? Makes you think they are. That little prepositional phrase, in their domains. That fits here. Now, then by combining that function, the theorem we just had, with this list, you can include a wide variety of elementary functions are continuous at every point in their domains. And that would be some multiply x to the n times sine x, and you can do all sorts of other things with this, as long as every one stays within its domain, that you can then have the nth root of sine cubed. That would be perfectly fine. So you can just expand these greatly. Now I'm certain that all of you, no, I'm not certain of that. No, we haven't got there yet. I was thinking of another class. Later we're going to add 2 other classes of functions here. What are we missing? Anyone know already? You aren't supposed to know, but exponential functions, they'll be continuous everywhere. And log functions, continuous only on positive values, not even 0 values. This is continuous at 0. Log functions will not be. So we'll add those 2, but that's coming later. Just a glance to the future. So by theorem 111, it follows that this is example 6. I think that's the next one. By the way, I failed to mention this sometime. This one has clarsoncalculus.com for an interactive version of this type of example. Not all the examples have those, but some of them do. Okay? So here's one of those combinations. F of x is equal to the sum of 2 continuous functions, x and sine x. X is continuous everywhere, sine x is continuous everywhere. So this will be a continuous function. Multiplying a multiplying a real number by a continuous function everywhere is continuous. Everywhere that function is continuous. You have to exclude the half pies because they are not included in the domain. Okay, how about this one? Be continuous. This one.
Except the
It's
cosine
continuous.
is 1.
Second?
The cosine is equal, if x is equal to 1,
Is x equal?
discontinuous.
Yeah. I think 0, no, not 0. Half pies. The half pies, that would make this 0. Okay, if x is a half pie, or minus half pie, or 3 half pie, or 7 half pies, or 17 half pies. All of your half pies, this would make that 0. So anywhere except where that denominator is 0, this will be continuous. See, they throw that little weasel word in there, you have to think. When would that denominator be 0? That would be 0 in half pies. Okay. So if you exclude those, continuous everywhere except for those points. Okay. Now, the next theorem, this is the one at the bottom of page 79. As a consequence of theorem 1.5, which is way, way back, allows you to determine the continuity of composite functions. It wasn't that far back. Okay. And this would just be f of x equals sine of 3x. That would be continuous everywhere. Why? Because 3x is continuous everywhere. It's a polynomial function. Continuous everywhere. No limitations on that at all. And sine is continuous everywhere, so that would be f of x would be continuous everywhere. Because the input for this g of x here, is continuous everywhere and would have a value. And sine is continuous everywhere, so any of the values 3 of x spits out, sine can take in. How about this one? f of x equals x squared plus 1. Where is that continuous? Only thing that gives you a little heartburn on this one. Second?
Everywhere?
Everywhere. Well, wait a minute. That's an even index on this exponent, isn't it? And what does that restrict? Thing in here has to be greater than or equal to 0. But guess what? It's always greater than or equal to 0, because any real number you put in here, you square it, it's going to be positive, or 0. 0 would be okay. But then you add 1 to it, it's all positive. So this one has no limit. It's continuous everywhere, even though it has an even root, because the argument of that even root, that g of x, the composite function part, is always positive. So if its output's always positive, your input for the square root, you don't worry about it. How about this one? Is that continuous everywhere? Anyone see? No. Where is it not continuous? When x is 0, certainly. That's the composite part. The g of x not even defined there, so it can't be at x equals 0. But not only there, oh boy, this is going to take way more thought than I want to do today. At 2 over pi, it's also not continuous, is it? Because if x equals 2 over pi, 1 over x is pi halves, and tangent is not defined at pi halves, right? Because that's one of your half pi's. So you'd also, not only x equals 0, not in the domain of the g, but then your x can't also, how would you say that? X also can't be any 2 over n pi, where n is any non-zero integer. Okay, I think that's how you say it, something like that. So here's theorem 112, continuity of a composite function. If g is continuous at some value c, and there we would have our g being 1 over x, so it couldn't be 0, for it to be continuous at that. And f is continuous at g of c, so as long as c wasn't, g of c was not pi halves or any half pi, so because f has to be continuous there, then the composite function given by f composed with g of x, which is f of g of x, is continuous at c. So you have to have that g is continuous at c. In that case, 0 would be excluded. And then f is continuous at g of c, and that means you'd have to exclude all the values of x that would make tangent discontinuous. Okay, so that would be your 2 over pi, 2 over 2 pi, 3 pi. No, not 2 pi. 2 over odd pi's. That's what you do. That would work. All right. All right, this one is quite as complicated as the first one was, as the pre-examples were, but okay. Oh, and by the way, the theorem 112 that we just had here, there is at least, I guess it's a total proof. I was going to say a partial proof, but that may be everything you need. So all of you who are going into mathematics, pure mathematics, pay attention to the proofs. The rest of you going into engineering, you probably should pay attention to them, but you'll never use them. I don't think. I hope not. Well, never mind. Okay. So let's do example 7. Describe the intervals on which each function is continuous. Describe the interval for x, for f of x equals tangent x. Hopefully I've said it often enough that should come right to mind.
Half pies.
Okay, any interval not containing a odd multiple of half pi. Okay. I'll let them write it for you. Okay, how about the next one? G of x is a piecewise defined function. It's sine of 1 over x when x is not equal to 0, and it's 0 when x is equal to 0. Is that continuous everywhere? Or, no, it says describe the intervals over which that is continuous. Any thoughts on that? Here's my gut feeling on it. Any of you have a feeling you want to err? Not E-R-R, but A-I-R. Okay. This isn't helping you much here, because as x is approaching 0, say from the left-hand side, what is 1 over x doing? Just the g, not the g, the inner function, 1 over x. What's that doing as x approaches 0 from the left-hand side?
Smaller.
Yeah. Good time. I mean going to negative infinity. Negative 4,485,000. Negative 784 trillion. You know, it's just getting more and more and more and more and more negative. Okay. And then what's the sign doing as the number is getting more and more and more negative? It's just going back and forth and back and forth and back and forth and back and forth between plus and minus 1 without any end to it. Just do that. The bigger the number, it just keeps going back and forth between plus or minus 1. So it doesn't really help to give us a value there, because the odds are it's still going to not ever be continuous there. And if you go from the right-hand side for positive, getting closer and closer to 0, again, this number, that is getting enormously large, and at enormously large numbers, sine is still going back and forth and back and forth and back and forth and back and forth between plus and minus 1. So it really doesn't do you any good to give it a value there. This thing is still going back and forth and back and forth and back and forth between plus and minus 1, never reaching that as a limit or anything as well. So this is continuous anywhere. Okay. As you said, this is continuous at any value not including a half pi or any odd multiple of a half pi. Okay? This is anywhere the x is greater than 0, anywhere the x is less than 0, but never. This doesn't help you. This does not close the gap and make it value. How about this one, however? I think we mentioned this before, didn't we? No. Sorry. That wasn't quite the same. No, I'm sorry. I was thinking sine x over x. This one has hope, because this is what we call, with piecewise defined function, this is an envelope function. If you think of sine, it's a periodic function, right? Now, as x, this is a constant function here. It's either an x is positive, it's doing like this, or negative, it's doing like that, okay? So basically, this then takes this up and down behavior of sine x and keeps it inside the envelope of these two lines here. As x is approaching 0, this half of it, that's the identity function, or the negative of the identity function. So x stays between those two, and the closer it gets to 0, then the smaller and smaller it gets because of this. This stays between plus or minus 1, but this gets infinitely close to 0. If you define that as a value there, I think that will then fix it for you and say, yeah, we know closer and closer to zero. This one has to be getting close to zero, but it doesn't have a value there. This gives it a value. So I think that one will fix it for you. Let's see. The tangent function is undefined all your half pi's. Any odd multiple of a half pi. Okay? 1/2 pi plus n pi, where n is any integer. All other points is continuous, so in any domain that doesn't contain a half pi is continuous. Okay? That one we got. This one, oh wait, same one. Oh, this is just showing the graph of it. So as long as you're between any of your half pi's, you're continuous there. You just can't include any half pi, because that blows up. It's going to positive infinity in one direction, negative infinity in the other. Near the twain should meet. Okay. So any of those intervals or any subinterval that doesn't cross the boundary, those will be continuous. Okay? This one, 1 over x is continuous except for x equals 0. The sine function is continuous for all real values of x. So this is continuous at all real values of x except x equals 0. Nothing is going to make that come to any resolution at x equals 0. This thing just keeps going back and forth, back and forth, back and forth. So still, that governs. Now, it's interesting what they're going to say. Oh, here we go. And here's the example. They love this. They love using this as an example. The g of x does not exist on both sides. And they don't have to be at all related, but they're just, going closer and closer, but still going between plus or minus 1. Okay. So g of x not continuous. It's continuous on this side and continuous on that side, but not continuous at 0, x equals 0. So your sine can't be continuous there either. Okay. Now, the c part. This function is similar to part b, except that the oscillations are damped, be sure you put the p in there, by the factor x. Okay? Now, and here we use the squeeze theorem. Okay? Minus the absolute value of x, because sine of 1 over x, as weird as that thing is, as long as x is not 0, that's still defined. This is going to stay between plus or minus 1. So the minimum it'll ever be is minus x, and the maximum it'll ever be is plus x, because this is always between plus or minus 1. So the minimum is going to be here, the maximum is going to be there, plus 1. As long as x is not 0. Okay? Now, this one is continuous. It doesn't have a value at x equals 0, not defined, but it's between these two absolute values of x. And as x gets closer and closer to 0, this one has to get closer and closer to 0. Because this is going to 0 as x going to 0. This one's going to 0 as x is approaching 0 from the right or left. Yeah. This one has to be squeezed in between. And as long as you define it as that value, which they did, then it has a value. Okay? So that piecewise defined function does. This has no value x equals 0, but this one does. And that's where the other one's headed. So you can do that. So that one does too, because of that, what I call the envelope function. The other thing, sort of weird way to say this, I guess, this is sine of some function here. This is the amplitude. So here we have a variable amplitude, and that variable amplitude is 1 to 0. So the whole function has to be. Okay. Really interesting stuff, right? But is it very practical? Well, it may be in certain circumstances. Okay. Now we're ready for intermediate value theorem. One of the key ones in all of calculus. Okay? Theorem 1.13. An important theorem considering behavior functions that are continuous on closed intervals. Okay? What we've been talking about. If f is continuous on some closed interval a to b, here's a, here's b, is continuous everywhere in there. As long as f of a is not equal to f of b. So if f of a is here and f of b also is there, you can't use this theorem. But if there anything, f of b could be greater than, f of a could be greater than, doesn't matter as long as they're not equal. And k is any number between f of a and f of b. So if f of a is up here, f of b down here, k is anything in between. Or if f of b is up here and f of a is down here, and k is any number in between. Whichever is on top, it doesn't matter. K is just some number between f of a and f of b. Of course, can't be any number if they were equal to each other. That's why you can't have them equal. Then there is at least one number c in that interval a to b such that f of c is equal to k. If k is in between f of a and f of b, and c is in between a and b, for any c in this, and remember these are continuous functions on that closed interval, then there's some value, maybe more than one value, where f of c is equal to k. Got to be, because they're continuous. You can't go from here to there, or there to there, and not cross every value in between. Can't happen, okay, if it's a continuous function, because you have no holes, no gaps. The intermediate value theorem tells you that at least one number c exists. It doesn't give you a method for finding that c. It just says they're there. It's called an existence theorem, okay? Does exist, but we don't know how to get there. Proof of this theorem is based on a property of real numbers called completeness. And for you pure mathematicians, I'm sure you've dealt with that before. Okay? The intermediate value theorem states that for a continuous function L, if x takes on all the values between a and b, then f of x must take on all the values between f of a and f of b, whichever is greater or lesser. And, you know, it could take them on several times, but it will take them on at least once. Okay. As an example of that application of the intermediate value theorem, consider a person's height. Okay? Consider your height. From the time you were a baby and they measured you and you were so many centimeters or inches long until you got to where you are today, and a few of us may have gone up and then come down some. The rest of you are probably still on your way up or stable, okay? But guess what? A girl 5 feet tall on her 13th birthday and 5 feet 2 inches tall on her 14th birthday, guess what? There was some age in between those two ages, 13th and 14th birthday, where she was 5'1", or 5 foot a half inch, or 5 foot 1 1/4 inches, you know, or whatever. There was some time. She just didn't jump. I mean, no matter how fast she grew, there was some time. May have been overnight one night, but she was there was some time when she was every height in between 5 feet and 5'2". Then for any height between 5 and 5'2", there must have been a time t, 13.07, or sometime when her height was exactly h, whatever that was. This seems reasonable because human growth is continuous. There are no jumps. There's no discontinuities there in your growth. And a person's height is not abruptly changed from one value to another. It's always gradual. Okay. Intermediate value theorem guarantees the existence of at least one number c on the interval a to b. There may be, of course, more than one number for which that would be true. So if this is f of a up here, and there's f of b down there, here's a and b, of course, there. And here's your function. At any value k, that could have been 1, 2, 3, or more values. Okay? There's at least one. And then your function straight there, one and only one. So if alpha is continuous on a to b, there is a, with this one, there's at least 3 c's, such that alpha of c is equal to k. That there's exactly 3 c's. Function that is not continuous does not necessarily exhibit the intermediate value theorem? It may, but it won't necessarily, okay? For example, the graph of a function here jumps over a horizontal line y is equal to k, never crosses it, so therefore it can't have, it can't meet the mean value theorem. Just, it's never required. Now I said it could, okay? If you imagine that this comes down like this, and then goes up like this, well, yeah, it has a value a couple of different places, but just because it meets the, it does have a value there, it doesn't make it continuous. Okay, so it's a discontinuous function, does not guarantee there's going to be a value C in between A and B, such that f of C is equal to K. That's all it says. Okay. Any questions on that? All right. Intermediate value theorem can often be used to locate zeros of a function that is continuous on a closed interval. Okay? What's required? Okay? The zeros of the function. If you can find some value that f of c, that value here, f of x is positive here, negative there, but you know it's continuous, got to cross zero somewhere in between. Now you can start bracketing. And as you bracket, you can get closer and closer. Specifically, if f is continuous on a to b, and f of a and f of b are different in sign, or any values in between there are different in sign, the intermediate value set guarantees the existence of at least one zero on the closed interval a to b, or any smaller interval that have difference in signs. So here's example 8, which I think is top of page 82. Use the intermediate value theorem to show that the polynomial function f of x equal x cubed plus 2x minus 1 has a 0 on the interval 0 to 1. Okay? What would be your first step to show that? Okay, pick one.
0.
I love it. Okay, because that's included here, right? So what's f of 0? Negative 1, of course. Okay. What is f of 1? Oh, I'm sorry. I should have had you pick another one. Want 1? Good choice. Okay.
2.
Second? You're picking one. Oh, yeah. If you pick this 1, then this will be plus
2.
Yeah, minus 1 is 2. So there you had a negative at 0, positive 2 at 1. You just show it. It has a 0. This is a continuous function. It's a polynomial function, continuous everywhere. Specifically on that interval is continuous. And since f of 0 is negative and f of 1 is positive, it has to have a 0 somewhere on that. May have more than one. Who cares? Okay? Maybe someone cares, but all we were asked to show it has a 0 there. We don't know what it is. Any of you think you can calculate it very quickly? Probably not. That's not factorable as I can tell, okay? Number one, it's cubic, that's really hard to do. So it's going to take some effort to find that 0, unless you have a graphing calculator, of course. Yeah, that's all you reach for it, okay? So, yeah, you can get a good estimation of it. Perfect. Let's see what they do. Note that f is continuous on the closed interval. Why? Why is f continuous? Why can't you say that? It said note it. Why can you note that? What kind of function is it? And polynomials are continuous everywhere, including 0 to 1. Okay? Never will a polynomial function have any gaps. They're smooth and continuous. Two features of polynomial functions. Continuous everywhere. So specifically they're continuous there. So they just chose, just like you did, One endpoint was -1, the other endpoint was +2. You know that, the alpha 0 is negative, alpha 1 is positive, so therefore it fits the criteria. You apply the intermediate value theorem. There's got to be some value, alpha c, that makes that true. And they pulled out their graphing calculator and graphed it and saw that, yeah, there's one, and in this case, only one value c. It looks like something between, say, 0.4 and 0.5, yes. That's just a guess, that it is equal to 0. All right, any questions on that? All you have to do here, it's just an existence theorem. Doesn't give you a value, it just tells you one exists, and it does. Now, how do you get a value from it? One method, not the best method, is called the bisection method. We're approximating the real zeros continuous function, similar to that used in example 8. I don't even remember example 8, somewhere back there. If you know that a 0 exists on a closed interval a to b, which we know now, okay, then the 0 must lie in the interval either between a and halfway between a and b, or between halfway of a and b and b. Unless, of course, the 0 is right there at the halfway point. Okay? If you find it is, you find your 0 and stop right there. But if the midpoint is not 0, then it's either positive or negative, right? And if this were, our example was negative here, if this is positive, forget this. Do these two, and then go halfway between those two. And then if it's negative, then go to those two. If it's positive, then do those two. And just keep doing half the point, halfway between, and then pick the interval where it does cross 0 and keep going. From the sign of alpha, the midpoint, you can determine which interval contains a 0, the left one or the right one. By repeatedly bisecting an interval, you can close in on the 0 of the function. And if you're clever about it, you can probably do better than bisecting. Okay? So be clever. Save yourself some effort. Have I discussed with y'all before my definition of a good mathematician? Did I talk about that? Has to be just a tad bit lazy. Do any of you qualify? No, you're all hard workers. You can still do it. Oh, he almost qualified. Okay. You can still do it. Don't get discouraged. But if you're lazy, you're going to find easier ways to work a problem. That's the sign of a good mathematician in my mind. That's just my opinion. You are a mathematician. You can contradict me here if you wish. Whoa! They didn't give an example here, just that one. Or they show at the bottom of the page, use your graphing calculator. It's even better than the bisection method. But if you don't have a graphing calculator, and we'll get to it hopefully in this course, I think we will. But ultimately you'll get to Newton's method, which is way faster than the bisection method. That gives you something to look forward to. Bisection method is sort of like good old Archimedes, who was one of the greatest ancient mathematicians of all time. Probably ranks right up there with Newton and I think probably Gauss or Euler probably. Yeah, there's several really great ones. But good old Archimedes, he was as much engineer as he was mathematician, though. He was approximating an area of the circle, and he did it by subscribing and circumscribing regular polygons inside and outside of a circle. And he could do the area of that polygon. And then he could take the average, and though the circle was somewhere in between there, he could take the polygon up as many sides as he wanted to. The math got tedious but doable, okay, and kept estimating or calculating the volumes and knowing it was in between those two. And he called that method the method of exhaustion, okay. to me, that's what limits are. You know, if you do it any other way, it's the method of exhaustion. The numerical way, graphical way. Find Bill's little tricks, you know, so you can do it analytically and close in on it much quicker. Well, bisection method is an exhaustion method. Newton's method, much faster. And graphic calculator is really fast. All right, homework exercises 1.4. Any of the odds. Okay, I thought I saw something. Any of the odds 5 through 9, they're all at calcchat.com. 5 is at CalcView. Oh, did anyone need that last slide any longer? I didn't mean to shut it out. If I ever go through a slide too soon, stop me. You know, I don't mind leaving it out there. Any of the odds 5 through 9, all at CalcChat, 5's at CalcView. Any of the odds 11 through 29, they're all at CalcChat, only 11's at CalcView. Any of the odds, either 31 or 33, they're both at CalcChat, 31's at CalcView. Either 35 or 37, they're all at CalcChat, they're both at CalcChat, 35's at CalcView. Any of the odds 39 to 57, they're all at CalcChat, 47's at CalcView. Any of the odds 59 through 63, they're all at CalcChat, 61's at CalcView. Any of the odds 65 to 69, they're all at CalcChat, 67's at CalcView. Either 71 or 73, they're both at CalcChat. Now this says you need a graphing utility. See if you can figure it out without one, but if you got one, by all means use it, that's fine. Both of those are at CalcChat, neither one are at CalcView. Any of the odds 75 to 81, they're all at CalcChat. Either 83 or 85, they're both at CalcChat. 87 should be at CalcChat. Any of the odds 89 to 93, they're both at CalcChat. Any of the odds 95 to 99, they're all at CalcChat. 95's at CalcView. You can look over 101 and 103 if you'd like. They're exploring concepts. I don't know if they're at CalcChat. They should be, but if not, you decide whether you want to chase them down or not. There's some true false here. Any of the odds 105 to 109. I don't usually like true false questions as a test question because you can make a question so close to truth but have one word and one interpretation of one word that might make it false. You don't know, is that what he's getting at or is this what he's getting at? So I don't like to use them, but still they're not bad to do here because you think through the issues, especially if you use CalcChat, if they have those answers. 111, you can think about doing that one if you'd like, and 113, you can think about that one. Oh, there's more, sorry. I'd say any of the odds 113 through 115 are, you can do either of those if you like. They should be at CalcChat. 117 is a proof, which, especially if you think you might be needing this kind of stuff in the future, focus on that one if you need it. Any of the odds 119 through 127, I guess. So any of those, they should all be at CalcChat. Now, I'm going to point out a couple. 120, I'm sorry, I said 120, I was focusing on that. Back from 119 to 127 is what I meant to say, whatever I said. Looking at 120, well, actually 118, the Dirichlet function, we mentioned that already, so I'm not going to go over that again. It may be Dirichlet, but since he's German, I'm guessing it's Dirichlet, or something like that. Okay, 120 is a signum function. If someone really is into that kind of stuff, who came up with this? What's it used for? You know, what is the practical applications of it? That could be a decent paper topic. I usually look for things like that. So, and then of course they always have the Putnam challenge, or not always, but most of the time at the end. And I don't know if the odd number is at CalcChat or not, but those are usually pretty tough problems. And if you are doing things like, well, I don't know, it's for a prize, but if you're doing something like advanced placement, which I doubt if you're doing since you're already in doing a college course? Why are you doing it? No, okay. Those may be things that people doing a placement would be interested in. All right, but that finishes. Ooh, and it also sounds like we've run out of time, doesn't it? In fact, we went over a bit, didn't we? Sorry about that, but I guess the good news is there's no extra charge, okay? All right. We'll begin with 1.5 next time. I had hoped to get started on that today, but I didn't. What's that?
Since we have a goal for 1.5 this Wednesday, that's going to be on Tuesday.
Okay, a little out of my ear, so that.
Since we have to go for 1.5 this Wednesday, test is going to be on Tuesday. Next Tuesday.
Okay. If we don't finish 1.5, we go.
No, I mean, since we have to go over 1.5 this Wednesday, the test is going to be on Tuesday.
Okay.
If I'm asking.
Yeah, okay. What I'll do, however far we get on 105, on 1.5, I'll give you the test so you can start working on it, even if we haven't finished everything in 1.5. You have at least a week to turn in the test, and I don't start the clock on that until we finish the chapter. I'll go and give you the test so you can get started on it. Why waste a weekend, huh? You want to use your weekends productively, right? So I'll give it to you on this, no matter what. Yes, sir.
Will the test be where you can't open it until you're ready to take it?
No, it's take home. It's
But not open book.
It's open book. Absolutely.
Oh, it is?
Yeah. I don't know, you work somewhere, right?
Yeah.
Okay. Do they ever say, okay, you can't use anything if you're figuring this problem out for me? No, you use everything you got at your fingertips, right? So the same thing here, you know.
Okay.
I want to measure how you use this stuff, not how much you memorize of the stuff. That to me is not. A lot of people teach math that way. To me, that's not math. Math is using it. So
Yeah. Okay.
I hope I'll make them tough enough that you have to work at it. Okay. All right. I'll try. Okay. I promise. Okay. Did that answer your question?
Yeah.
Okay.
I also have a question about the paper. Does the research subjects have to be from the math book? Or
No.
or it
Anything
just has to involve
that
math?
has involving calculus in some stretch of the imagination, have some application from calculus or have to do something with calculus.
All right.
All right.
Thank
Good deal. And remember, if you get it into me before the end of the month, you get those 4 bonus points. February, that goes down to 3. All right, let me end this.